Hi, thank you, everyone. So I'm just going to talk about the variation-aware design flow today and my own personal experiences with it. So some of the major challenges I saw in variation-aware design was, of course, hitting power and performance targets. Performance being the overriding concern in my particular application, but of course you need to minimize the power in order to be able to put your stuff on the chip. And of course, the removing the pessimism from the traditional design corners was also a major push for moving into a variation-aware design flow. Primarily to minimize the power was the big motivation for that, since we're under power constraints all the time. And then one of the other things that the variation-aware design flow allowed was a means of trading off the different circuit specs a little easier than you could do with other design flows, the traditional ones of corners and Monte Carlo. Some specs you can't really get with traditional corners, such as your INL or DNL of devices, of DACs, for instance. So you're required to use Monte Carlo in order to get that. But Monte Carlo is quite prohibitive in terms of time and simulator licenses. Some of the best practices for the variation-aware design flow that I'd observed is when you're working in traditional corner-based flow, you tend to not necessarily design for variations like mismatch. So certain things, when you're designing a latch, for instance, that can have its offset taken out, you need to design your simulation deck in order to remove that offset before you start characterizing the design. So that's one major change from a traditional corner-based methodology that you'd have to do, where you do corners first and then go back and do Monte Carlo to get the specs that you couldn't get with corners. The other thing, other best practice that I come up with is in the variation-aware design flow using fast Monte Carlo in Solido. That does your Monte Carlo simulation, but it also gives you a set of points or a set of corners that you can pull out that includes things like mismatch of the devices. So you can get your duty cycle distortions or things that rely on local mismatch in order to be able to accurately represent the spec. So you can use their 3 sigma corner extraction or n sigma corner extraction flow, or a quicker turnaround that I started using in the flow was to run the Monte Carlo and then just pick the points that gave me the worst case that were around the 3 sigma point. So you could get instead of taking a day or two to get your corner, you could get it in 6 hours, which gives you a lot quicker turnaround if you need to iterate on getting a new corner every time you make an update to a circuit, because some circuits, their characteristic can change quite a bit as you're tuning the circuit. And then that leads into the third point of using the Solido design sense in order to help with optimizing the circuit. So you could modify your device sizes across a range of device sizes, and you could do it across however many devices in the circuit you had simulation time for. And that let you see the sensitivities in the circuit and gradually adjust the specs that you wanted to really focus in on and provide trade-offs as you're going through the optimization of the circuits. Some of the must-have features of a variation-aware design flow. You've definitely got to be able to generate simulation corners that are appropriate for each individual circuit, including the local variation as well as the global variation, in order to be able to optimize the circuit fully and perform the correct trade-offs on the circuit, because certain specs may not be terribly important as long as they're under a certain threshold, but other specs may be very important no matter what. And then, of course, the reason for needing these specific circuit-specific corners is the standard corners can be very pessimistic in some cases, and they cannot cover a spec at all in other cases. In those cases, you'd have to run Monte Carlo, which can be very expensive to run if you're having to iterate through a design. And then you need to be able to use those corners in what-if scenarios, like I described with the design sense in the previous slide. Another must-have from variation over design flow is being able to identify what devices are your critical devices in a circuit, and not necessarily just what devices, but what process parameters are a concern in a circuit. Sometimes you can run into surprises where, for instance, your contact resistance may be your dominant factor in a circuit, especially in these lower technology, lower feature sizes. So you may be thinking by making the device bigger, you're making it better, but in reality, you're not doing anything for the performance of the circuit, and you're only using power. And then, of course, ease of use is also a very important requirement of a variation design flow. You need to be able to easily analyze what-if circuit changes. You need to be able to visualize the results of those circuit changes so you can make educated decisions on where you want to push the circuit to get the best power performance trade-offs. And of course, you need to be able to visualize those trade-offs. It's very hard just looking at a set of numbers to figure out what you should do with the circuit. Some of the results that I was able to obtain with this flow, one of the high-speed comparators that I'd worked on, I was able to improve the evaluation time by about 30% in the 3 sigma corner, reduce the power at the same time by 30%, and then improve the latch sensitivity by about 50% from a previously tuned design. In the process of doing this optimization, it was done on post-layout netlist, which makes things a lot more challenging than a schematic-based netlist, but is necessary for accuracy. Since each simulation took about 2 or 3 hours per case, running Monte Carlo across a lot of different design conditions isn't really practical. But being able to take those Monte Carlo corners that you get out with Solido, I could run 1,000 different combinations of those devices across 10 different corners and do that in the span of about a week or two, which if I had tried doing that same thing with a 200-point Monte Carlo sim, which is what I used to generate the corners from, it would have taken about 3 months to do those same simulations. One advantage that quick turnaround time for optimization affords is you can then go through and modify your layouts, get a new post-layout netlist, and resimulate it and get more accurate results. So you can hone in on a finely tuned answer much quicker and much more effectively. And in this particular case, the number of corners I actually needed to characterize the design was less than our typical set of corners. So that actually helps quite a bit too.